The implicit neural representation, INR, has garnered considerable attention in recent years due to its ability to capture signals by preserving the mapping function from coordinates to corresponding attributes using neural networks. However, existing INR techniques are plagued by spectral bias, where low-frequency components of the signal are more easily learned. To combat this issue, researchers have proposed various solutions, including positional encoding, which embeds multiple orthogonal Fourier or wavelet bases into the subsequent network. Despite these efforts, a significant challenge remains. The frequency distribution of a signal to be inversely solved is often unknown, leading to a mismatch between the predefined base's frequency set and the characteristics of the signal itself. Moreover, the use of periodic or non-periodic activation functions has only alleviated the spectral bias to a frequency specified one, and inappropriate parameters initialization often results in a capacity convergence gap. The root cause of these problems lies in the underutilization of the definition domain in the used activation functions. Current activation functions have an infinite domain, but their nonlinear components are often concentrated on a small region centered around the origin. By interspersing narrow activation functions with different frequencies along the full definition domain and selecting the ideal one by controlling the range of input values, the supported frequency set could be significantly expanded, resulting in improved expressive power of current INRs. To address this issue, the authors propose the Finer++ framework, a universal framework to extend current activation functions to their corresponding variable periodic versions. The local nonlinear components are repeated many times along the z-axis, and the scale parameters of each local component are changed. This approach is distinct from previous explorations, which focus on optimizing the weight matrix for manipulating frequency candidates with better matching degree. Finer++ aims to provide a more flexible and efficient way to tune the supported frequency set, leading to improved performance in signal representation. The framework can be applied to various tasks, including 2D image fitting, 3D signed distance field representation, 5D neural radiance fields optimization, and streamable INR transmission. The authors demonstrate the generalization and capabilities of Finer++ with different activation function backbones, such as Sine, Gauss, and Wavelet. The results show that Finer++ improves existing INRs by addressing the spectral bias and capacity convergence gap. The proposed framework has the potential to significantly impact the field of signal processing and inverse problems, enabling more accurate and efficient solutions for complex signals with multiple frequencies. The Finer++ framework is proposed to address the limitations of classical implicit neural representations, INRs, by extending activation functions from periodic, non-periodic to variable periodic ones. This innovation enables tuning the supported frequency set by adjusting the initialization range of the bias vector in the neural network. Figure 1a illustrates the selected narrow activation functions in classical Sine, Gauss, and Wavelet, alongside the proposed variable periodic ones with different bias settings. The impact of varying initializations on the bias vector is demonstrated in Figure 1b, which plots the training curves of previous INRs and Finer++. The results show that, regardless of the backbone activation function used, both shift invariance and eigenvalues distribution of the neural tangent kernel, NTK, in Finer++ S version can be enhanced by increasing the initialization range of the bias vector. This allows for flexible tuning of spectral bias and significant alleviation of the capacity convergence gap. The Finer++ framework is evaluated through extensive experiments on 2D image fitting, 3D signed distance field representation, 5D neural radiance field optimization, and streamable implicit neural representation. These experiments build upon the preliminary exploration presented in CVPR 24, which identified three key characteristics of INRs: underutilized definition domain in activation function, frequency-specified spectral bias, and capacity convergence gap. Finer++ improves the utilization rate of the definition domain and addresses the latter two characteristics. The main contributions of this work include deriving and summarizing three characteristics of existing INRs, developing a universal framework Finer++ to improve the performance of current INRs, proposing a novel initialization scheme for finer and demonstrating that finer surpasses prior INRs activated with other functions. The related work section discusses implicit neural representations, including neural radiance fields or NRF, and their applications in various fields of vision and signal processing. However, current approaches often suffer from the well-known spectral bias problem, leading to suboptimal performance in fitting functions and ineffectiveness in various applications. The proposed finer framework offers a promising solution to these limitations, enabling more effective and efficient implicit neural representations. Implicit neural representations, INRs, face the spectral bias problem, which can be addressed through innovative strategies. These include spatial encoding, frequency or polynomial decomposition, high-pass filtering, and multi-scale or pyramid representations, all aimed at emphasizing high-frequency components of a signal before feeding it into the model. For instance, Fourier features mapped from spatial coordinates are used as input to multi-layer perceptrons, MLPs, to improve the performance of INRs in expressing high-frequency information. Architectural modifications, such as multi-scale network architectures with band-limited Fourier spectra, aid in capturing both low-frequency and high-frequency components of a scene. Automatic frequency tuning through nonlinearity activation functions has gained interest, particularly with the sinusoidal representation network, Sine, which uses periodic activation functions, especially sine functions, to represent complex signals and functions. Sine has demonstrated its effectiveness in representing intricate details and high-frequency components compared to traditional activation functions like ReLU or sigmoid. Other approaches, such as Gaussian-based and Wavelet-based activation functions, have also been proposed to improve Sine's performance. Moreover, introducing hash tables between the input coordinates and the neural networks can alleviate the spectral bias. Learnable multi-resolution hash tables, multi-shift windows hash tables, and dynamic hash tables have been proposed to improve the performance of INRs. These hashtable-based INRs outperform function expansion-based ones but have significantly increased storage overhead, limiting their applications in storage-sensitive tasks. INRs focus on pursuing the neural network to characterize attributes as accurately as possible. The pipeline of INRs involves a multi-layer perceptron, MLP, network, where the output of each layer is computed using an activation function. The activation functions used include periodic functions like sine, non-periodic Gaussian functions, and wavelet functions. Notably, existing works focus on designing activation functions with nonlinearity at a small region centered around the origin point, ignoring a wide range of areas far away from the origin point. This limitation is addressed by proposing novel activation functions that can capture nonlinearity in a broader range. Implicit neural representations, INRs, activation functions have been limited by their focus on n-online arities centered around the origin, underutilizing the definition domains of these functions. This characteristic is attributed to the periodic nature of the sine function, where only the central periodic nonlinearity is used, considering the convergence and performance of Sine. The expressive power of INRs is determined by empirical scale parameters, which scale the input values. However, removing or setting these parameters to 1 by default can significantly reduce performance, as specialized empirical scale values and initialization strategies are crucial for optimal performance. To address these limitations, a unified framework is proposed to extend existing periodic, non-periodic functions to their variable periodic versions, introducing the finer activation function. This framework aims to address the frequency specified spectral bias and the capacity-convergence gap. The finer activation function utilizes variable periodic functions for activating INRs, analyzing the behaviors of its supported frequency set and training dynamics under different initialization ranges from both geometric and neural tangent kernel perspectives. 3 key characteristics of INRs are highlighted. 1. Current designs focus solely on n-online arities centered around the origin, underutilizing the definition domains. 2. INRs exhibit a frequency specified spectral bias, determined by the chosen activation function and empirical scale parameter. And 3. Increasing the initialization range of network parameters can enlarge the function set that INRs can represent, but but violates the convergence guarantee, resulting in a performance gap. Experimental results compare the performance of various INRs with different initialization strategies for fitting a high-resolution image, demonstrating a performance gap between the standard form and the proposed initialization scheme. The importance of carefully designing initialization strategies for INRs is highlighted. Equation 2 presents a general form of the functions that can be represented by INRs, extending the activation function sigma x as polynomial functions, with the signal attribute as a one-dimensional scalar. Equation 3 provides specific examples for Sine, Gaussian, and Wavelet activation functions. The limitations of existing INRs, including the capacity-convergence gap, are discussed, and the finer ++ activation function is proposed as a solution. The behaviors of finer ++ supported frequency, set and training dynamics under different initialization ranges are analyzed, providing insights into the performance of INRs. The proposed finer ++ activation function addresses the limitations of existing INRs, including the capacity-convergence gap. The results highlight the importance of carefully designing initialization strategies and activation functions for optimal performance in INRs. The finer ++ framework introduces a novel approach to extend continuous periodic or non-periodic functions into their corresponding variable periodic forms. This aims to mitigate the inherent limitations of existing activation functions in deep neural networks. Variable periodic activation functions, denoted as sigma p, x, are defined for both periodic and non-periodic functions. For instance, when Sine, Gaussian, and Wavelet functions are used, their corresponding variable periodic forms sigma Sine, sigma Gauss, and sigma Wave are defined accordingly. These functions exhibit increased frequency along the z-axis due to the x+1 term, resulting in nonlinear components existing everywhere along the z-axis. This approach addresses two limitations: capacity-convergence gap and spectral bias. The selection of the frequency increase parameter ωf is crucial to avoid issues such as degeneration and overlap. An empirical value of ωf equals 2.5 is used for subsequent experiments. The initialization scheme for the bias vector is also crucial due to the non-convex nature of variable periodic activation functions. Proper initialization is necessary to avoid local minima and ensure convergence to the global optimum. Overall, the proposed finer ++ framework and variable periodic activation functions aim to address inherent limitations of existing activation functions and improve the performance of deep neural networks. The finer ++ model, a variant of the Siren model, employs a novel initialization strategy for the bias vector B. By leveraging a uniform distribution U-k, with a larger range k than traditional methods, the initialization of B becomes more flexible, allowing for a more effective tuning of the supported frequency set. This enhanced flexibility, in turn, enables better utilization of other nonlinear components in the variable periodic function. From a geometrical perspective, the authors demonstrate that the supported frequency set f(0) k expands as the initialization range of B increases. Notably, the supported frequency set fp in previous INRs is a subset of f(0) k in finer ++. This indicates that finer ++ can capture a broader range of frequencies, thereby enhancing its representation capabilities. The authors also provide insights into the neural tangent kernel (NTK) perspective, where neural network training is viewed as kernel regression. By analyzing the diagonal property and eigenvalue distribution of the NTK, they shed light on the convergence of the network in fitting signals. This analysis is crucial for understanding the training dynamics of neural networks and the implications of the proposed initialization strategy. The use of a larger initialization range for B in finer ++ allows for a more efficient exploration of the frequency spectrum, ultimately leading to improved representation capabilities. This, combined with the NTK perspective, provides a more comprehensive understanding of the model's behavior and its potential applications in various fields. The neural tangent kernel (NTK) of the finer ++ model, an extension of the INR model with a Sine activation function, is discussed in the paper. The NTK is calculated using the definition provided, and it can be observed that the scaled term is approximately proportional to the absolute value of bias, B, for all nodes of the kernel. However, the change rule of the Sine term for diagonal elements differs significantly from non-diagonal elements. The diagonal elements k, she, are increased with the increase of b, while the non-diagonal elements k, she, xj, can be very small, appearing as a diagonal enhanced kernel. This property provides better shift invariance, as the coordinates in the training set are little coupled with each other during the training process, thus the signal could be better learned. In the figures provided, the left four subfigures in the first row visualize the NTKs of finer ++ with Sine activation for learning a 1D signal with 1024 coordinates. It is observed that the diagonal property of NTK is enhanced with the increase of initialization range of B, verifying the analysis mentioned above. The rightmost subfigure visualizes the changes of eigenvalue distribution, and it is observed that the number of eigenvalues is increased with the increase of B. The performance of finer ++, a type of implicit neural representation, INR, is significantly influenced by the initialization range of the bias vector. By widening this range, the authors demonstrate a substantial reduction in error and improvement in image representation. This finding is further supported by an analysis of neural tangent kernels, NTKs, and eigenvalue distributions for various activation functions. Notably, a larger initialization range is associated with an increase in the number of large eigenvalues, which is a desirable property for INRs. The selection of parameters is also a crucial aspect of finer ++, and the authors provide a detailed comparison with previous INRs. The results show that finer ++ exhibits enhanced robustness in parameter selection, making it a more reliable choice for a range of applications. To demonstrate the versatility of finer ++, the authors apply it to several tasks, including 2D image fitting, 3D signed distance field representation, 5D neural radiance fields optimization, and streamable INR transmission. These experiments highlight the potential of finer ++ to be used in various domains, from computer vision to computer graphics. The author's analysis of NTKs and eigenvalue distributions provides valuable insights into the behavior of finer ++ and its underlying mechanisms. Specifically, the increase in large eigenvalues with a larger initialization range is a key factor contributing to the improved performance of finer ++. By understanding these relationships, researchers can better design and optimize INRs for specific tasks and applications. Overall, the findings of this study demonstrate the importance of careful initialization and parameter selection in INRs, and highlight the potential of finer ++ as a robust and versatile tool for representation learning. Finer ++ is a novel method that significantly outperforms state-of-the-art baselines in image fitting tasks. Quantitative evaluation results on a widely used natural dataset, comprising 16 images with 512 x 512 resolution, shows superior performance in terms of peak signal-to-noise ratio, PSNR, structural similarity index measure, SSIM, and learned perceptual image patch similarity, LPIPS. This achievement is attributed to the L2 distance loss function used during training. The method's performance is influenced by the initialization range of bias vectors. As the range increases, so does the supported frequency set of finer ++. This behavior is demonstrated through error and spectrum maps of learned images using finer ++ with different activation functions, such as Sine, Gaussian, and Wavelet. The visualization of output from neurons in the first layer of finer ++ and previous INRs reveals that finer ++ neurons exhibit more diverse frequency encoding, indicating a more efficient representation compared to previous INRs. The analysis of finer ++ behavior under different initializations provides valuable insights into the importance of initialization range in controlling the supported frequency set of finer ++. Overall, the results demonstrate the effectiveness of finer ++ in image fitting and its ability to capture a wide range of frequencies, outperforming state-of-the-art baselines. Finer ++ demonstrates superior performance in representing signed distance fields compared to 4 classical INRs: PEMLP, Siren, Gaussian, and Wire. This is evident from Table 2, which presents quantitative comparisons on shape reconstruction tasks. Finer++ achieves lower chamfer distance and higher IOU scores, indicating improved performance. Combining Finer++ with different activation functions, Sine, Gaussian, and Wavelet, results in significant improvements over their corresponding baseline methods. For instance, Finer++, Sine, outperforms PEMLP, Siren, and Wire by achieving an average chamfer distance of 3.559 × 10⁶ on the armadillo shape. This pattern persists across multiple shapes, underscoring the advantage of the proposed framework in reducing neuron waste by representing multiple frequencies. The average values further solidify Finer++'s leading position among tested frameworks. Neural radiance fields, NRF, aim to learn a 5D mapping function f. R5 right-pointing arrow R4 that maps a 5D coordinate opening parenthesis x, d to its 3D color C and 1D opacity sigma, enabling realism and scalability for embedding different rendering processes. This involves calculating the ray function in 3D space using camera matrices, sampling points along the ray within a predefined depth range, and feeding the direction and position coordinates into the implicit neural representation, INR, to query the radiance value, C, sigma. The color C, P, of a pixel is then calculated using differentiable volume rendering. The rendering technique employs the following equation: C, P, equals n-ary summation, I equals 1 to n, T underscore I, 1 express, sigma underscore I delta underscore I, C underscore I where T underscore I equals express, n-ary summation, J equals 1 to I1, sigma underscore j delta underscore j, and delta underscore I represents the distance between neighboring sampled points. To evaluate the Finer++ method, a comparison is made with 4 classical methods using different backbones: Sine, Gauss, and Wavelet. The experimental setting follows Wire, using only 25 training images instead of the commonly used 100. The results, presented in Table 3 and Figure 11, demonstrate that Finer++, Wavelet, achieves the best performance in almost all 8 scenes of the Blender dataset. Additionally, the results show that applying Finer++ improves the performance of all backbones. Figure 11 provides a qualitative comparison, highlighting the advantage of Finer++ in representing high-frequency components. For instance, the reconstructions of the truck frame using other methods oversmooth the holes, red boxes, and highlights, green boxes, whereas Finer++ preserves these details. This demonstrates the effectiveness of Finer++ in capturing high-frequency components, which is essential for realistic rendering. The use of only 25 training images, instead of 100, allows for a better verification of the advantages of Finer++ in representing high-frequency components. The results suggest that Finer++ can be a valuable tool for improving the performance of classical methods in rendering tasks, particularly when high-frequency details are crucial. The proposed method, Finer++, demonstrates its efficacy in novel view synthesis tasks through the evaluation results presented in Table 3. A comparison with various baselines, including PEMLP, Siren, Finer++, Gaussian, and Finer++, Sine, is conducted on several scenes. Quantitative evaluation is performed using metrics such as PSNR, SSIM, and LPIPS. The results indicate that Finer++ achieves superior performance in most cases, outperforming the baselines. For instance, on the chair scene, Finer++, Wavelet, achieves a PSNR of 33.78, significantly surpassing the second-best result, Finer++, Gaussian, which obtains a PSNR of 33.49. Similar trends are observed on other scenes, including drums, ficus, and mic. Notably, the wavelet-based variant of Finer++ generally performs better than its Gaussian and Sine counterparts. In terms of SSIM, Finer++ demonstrates comparable performance to the baselines, with some slight improvements on specific scenes, such as the chair scene, where Finer++, Wavelet, achieves the highest SSIM score of 0.975. Regarding LPIPS, a lower score indicates better performance. Finer++ consistently achieves lower LPIPS scores than the baselines, demonstrating its effectiveness in capturing nuanced scene details. Qualitative comparisons are presented in Fig. 11, which provides a direct assessment of the rendered scene quality and helps evaluate the method's capabilities. Finer++'s results suggest its competitive edge over the compared baselines. While maintaining superior PSNR performance, it offers robust scene reconstruction and reduced distortion. Its benefits extend beyond just rendering visual information accurately to efficiently providing refined detail structures of captured objects within specific images and sets. This is achieved through continued effort for model validation refinement with reduced dataset handling requirement efforts of relevant scope over input constraints. The authors introduce a novel approach to streamable implicit neural representation, INR, transmission, leveraging the Finer++ architecture. This method addresses the challenges of distributing INRs to devices with varying resolutions or providing streaming services that require progressively decoding different signal components while ensuring consistency with transferred network parameters. The proposed approach involves a progressive training strategy, where a small, narrow network is initially trained to model low-frequency components. The network width is then increased, and additional network parameters are trained to capture mid-frequency components, while the parameters from the initial step remain fixed. This process is repeated to model higher frequency components. The authors analyze the limitations of the Sine network, which exhibits a frequency-specified spectral bias, limiting its expressive power for modeling high-resolution signals under this training configuration. In contrast, Finer++ is inherently suitable for building streamable INR, especially in cases where the signal has high resolution. The performance of Finer++-based streamable INR can be significantly enhanced by changing the initialization range of the bias vector in the widened network parameters. The pipeline of applying Finer++ in streamable INR transmission is visualized in Figure 13, where the initialization range of the bias vector is increased to represent high-frequency components better. The results, shown in Figure 12, demonstrate that Finer++, Sine, outperforms Sine in all training stages of streamable INR, providing more clear details not only in areas with different frequencies but also in all stages. The authors conclude that Finer++ addresses the characteristics of existing INRs, including underutilized definition domain in activation functions, frequency, specified spectral bias, and capacity convergence gap. The proposed approach has been demonstrated to have advantages over other INRs in image fitting, 3D shape representation, neural rendering, and streamable INR transmission. Future work will focus on designing INRs without any frequency specified spectral bias. Please provide the original transcript that needs refinement. I'll transform it into a direct, concise, and technically accurate summary suitable for voiceover narration, following the guidelines you provided. Please provide the content that needs refinement. I'll transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided. Dr. Xuan Cao is a prominent researcher in computational photography and image-based modeling and rendering. He received his BS degree from Nanjing University in 2006 and earned his PhD from the Department of Automation at Tsinghua University in 2012. His academic background is complemented by various visiting positions, including stints at Philips Research in Aachen, Germany, Microsoft Research Asia in Beijing, and the University of Texas at Austin. Currently, he is a professor at the School of Electronic Science and Engineering, Nanjing University. This extensive background and expertise have significantly contributed to the research area covered throughout the paper.